Daniela, we start again. Now it's my great pleasure to announce a lecture of Michael Oberguggenberger, a friend of us for many, many years. He's already domestic here in Novi Sad, professor honoris causa somehow of Novi Sad University. And he's the founder of Colombo theory, jointly with Colombo. But as a founder, he will present a new lecture about, I will tell the title, Fuzzy and Weak Solution to Partial Differential Equations. So his view to fuzzy set theory in the framework of partial differential equations. Let me say that Arpa Takachi also did some work in fuzzy set theory with Juzica, and so when we spoke, Mike Oberguggenberger and me, he just wanted to talk about that because of this fact. So, Michael, if you hear me, you can start.
I can hear you. Can you hear me?
Yes,
can you hear me
we see you. Hello,
okay.
Hello, Michael. Nice to see you.
Hello. Well, nice to see you all. It's a big pleasure to be in this conference dedicated to the memory of Arpa Takachi. And let me now try to share my screen. Okay. Oops. Can you all see my screen? Is it okay?
Good.
Okay. Then I will start.
Yes, we can see.
Okay, thank you very much for the comments, because I just see my screen and a few of you. But I have to get used to video conferences, obviously. Well, as Stefan said, this talk is a bit offbeat on fuzzy sets, which is not really the theme of the conference. Well, I have not worked in fractional calculus, so that's one of the reasons. But the other reason, as Stefan already said, is that Arpa was interested in fuzzy sets and has also written several papers, and we had many discussions over the years. So I think in the spirit of Arpa Takachi, this talk fits, as Judica will also confirm. Okay, so what is the plan of the talks? First, I think I should say a few things about fuzzy sets. Might not be so common in this audience. And the interesting thing is that originally fuzzy sets introduced with some forerunners by Lofty-Zadeh in the 1960s were invented for describing uncertainty and for mathematizing linguistic vagueness. Okay, so it has, there are a lot of applications from databases to controllers, etc., etc. But one thing is quite curious, that one can use these fuzzy sets also to model generalized functions. And as you see, this is a rather old idea of mine. I already talked about this in this conference, which you see on the bottom of the page. But I thought the idea are not so much known in the generalized functions audience, and that's why I thought it might be nice to talk about it. Okay, so I will fix on Burger's equation to explain the ideas, and then talk about existence and uniqueness of fuzzy solutions, then how to view generalized functions as fuzzy functions, and weak solutions as fuzzy solutions. So the next few slides will be on fuzzy sets. Well, okay, in set theory, which is rather well known, if you have a subset of some bigger set, capital X, then each element of capital X is either a member of the subset or not. So in this case, they indicate the function is 0 or 1. And fuzzy subsets, you have a certain indicator function, a membership function, which is between 0 and 1. So one can assign a certain great degree of membership to the fuzzy set A. Well, the language is a bit redundant because the fuzzy set and its membership function are the same, but it is useful to distinguish, so to speak, of the fuzzy set and its definition through the membership function. Well, all fuzzy sets I will use here are normalized, so they go from between 0 and 1. And just to be clear, the fuzzy set f of x is the collection of normalized fuzzy subsets of x. And as already sort of implied by what I said, classical crisp, which they call crisp in the theory subsets, are also fuzzy, where the membership function is just either 0 or 1. So that's a special case of fuzzy sets. Well, an important notion is the alpha level sets of fuzzy sets. That is the intervals or sets, subsets of capital X with the property that the membership function is greater than alpha. Okay, I will just show a few pictures. Here you see on top two fuzzy sets on the real line, capital X. So on the left, you see the interpretation as a degree of membership. So this little a, which I called x before, has a degree of membership pi of capital A in this set A. Well, this is a picture from another neighborhood, so this I called it M, but it is also often called pi because one can view this as the degree of possibility that the value A takes, this value A is taken by some variable. Okay, so here you see a fuzzy number where the level sets are intervals. And here the other interpretation, you see two level sets, A beta, A alpha. So if alpha is smaller than beta, then the level set is larger. And one can also view this as a set of intervals which have a certain valuation, namely 0 for the biggest possibility and 1 for this point up there. Could also be an interval up there. Okay, but one can fuzzify every set. So in particular, you can fuzzify function spaces. So here you see a fuzzy function. Here is time. Well, it comes from the solution of a fuzzy differential equation, which I will not show. So membership degree 1 is this oscillation with the black line, which you see here also on top. And here you see the level surfaces, level lines, and here you see a surface plot of this fuzzy function. So if you have any function down there, you can compute the degree of membership of this function to this given fuzzy function. Okay, so this is a short introduction to fuzzy sets, but we need two more things. One thing is that we can form the product of two fuzzy sets, the Cartesian product, and the membership function is just the minimum. That's one standard version of the membership functions of the one and the other. And here is a very important thing. This is kind of a transfer principle on which many of the arguments will rest. It's called the extension principle. And it says if one has a function from x to y, the classical sets, then one can extend it to a function on fuzzy sets in the following way. So if I have a fuzzy set A, I need to say what is the membership function of the image of A, f of A, in Y. And one gets it just by looking at the inverse image of this value Y, checking all x's that lead to Y, and then looking at the membership degree, and then taking the soup of all those membership degrees. Okay, so maybe at first sight it looks a bit strange, but this is an extremely essential kind of thing, and it has also a good interpretation in terms of possibility, because these x's which lead to y through f, they all have a certain degree of possibility. And the largest of them then sort of determines the degree of possibility that this y belongs to f of a. So I think it really is a mapping of this possibility measure, at least is some plausible interpretation. Okay, and then it also turns out that it is actually nothing but interval analysis, or more generalized set-valued analysis. The alpha level sets of the image are the images of the alpha level sets. So basically one can reduce on alpha level everything to set-valued mappings. Okay, so much about fuzzy sets. Okay, the Burger's equation you all know, I think, here with viscosity lambda. I on purpose put this on the left-hand side, and we have here some initial data. And I take the one-dimensional case, x is one-dimensional, t is greater or equal to 0, and lambda is, of course, some positive viscosity constant. And so the first question I will address here is, can we solve this equation in some sense when this lambda is now a fuzzy number and the initial data is a fuzzy function? So that's the first step. So one would like to have existence and uniqueness of a fuzzy solution. And we will have this. So to set up for the extension principle, I write the equation operator, which maps u, and also this lambda, which will be fuzzified. Okay, and the problem is that p of u lambda should be 0, and the initial data should be the given ones, right? Okay, of course, you see at this stage that this is very general. It doesn't have to be Burger's equation. Right? Okay, but let's stay with the Burger's equation. So we need function spaces to solve the equation. So one possibility is to take continuous bounded functions. So I'm looking for classical solutions at this stage. Two derivatives, then the initial data are a bounded continuous function. The parameter is the interval 0 to infinity, a positive number. Okay, and then the point is we also need the target space. So if I go back, you see this p u lambda is 0 somewhere, and this has to be specified in detail in this situation. And well, of course, here naturally, if I take two derivatives, etc., then I certainly end in the space of continuous functions here. Okay, so the classical problem, of course, it is well known by Hopf's formula that if you have u0 and u0 and lambda, then the initial value problem has a unique solution. And the equation is valid with 0 in the space of continuous functions. Okay, and now just to set up for the extension principle, we have to introduce operators which we can extend. Right? So one thing is that we have to separate here everything which is fuzzy. If it appears in an equation after substitution twice, I cannot say much about this. This is a special issue of fuzzy sets, and by the way, also of interval analysis. So I make everything into a differential equation. So we have u, and also the parameter lambda is now the solution of a trivial differential equation. Its time derivative is 0, and the initial value is lambda 0, so it is actually lambda 0. Okay, but now we have an extended system, and we can look at the equation operator. This is the left-hand side, which should be 0. Then we have the restriction operator, which maps the u, once we have it, onto the initial data. Then we have the solution operator, which maps the initial data and the parameter lambda to the solution. Well, the lower line is a trivial line, of course. Lambda 0 is just mapped to lambda 0, and the upper line is the solution. Okay, but as I said, for reasons of substitution of fuzzy numbers in equations, we have to introduce this lambda as a new variable. Okay, so we can now extend this. We can now The equation can be applied to fuzzy functions and fuzzy lambda here, which is also a function, a constant function. The restriction can be applied to it, and the solution operator can also be applied to it. So if we have initial data and a parameter which is fuzzies, then we get a fuzzy function as a solution. Okay, and the definition of a fuzzy solution is that the equation operator, the extended extension operator, should be 0, and the restriction operator should give the fuzzy initial data, right? Where this 0 is the crisp 0, so it is the 0 function which has just membership degree 1, if it is the 0 function, and otherwise has membership degree 0. Okay, so that's the extension of the classical concepts to the fuzzy setting. Okay, and then one can see that if we have some initial data, which is a fuzzy subset of continuous functions and parameters, then the prolonged system has a unique fuzzy solution. Well, I gave you a sketch of proof, but if I look at my watch, I should not give it here. So it is just a few words. It is sort of a quite different flavor to prove such things. So one has to prove that, so for example, that the initial data are taken is just triviality because the extension principle is functorial, okay, which is very nice. And okay, to show that the equation is satisfied by this fuzzy extension, you have to play with some suprema. Let me not go through this. For the uniqueness, you have similar arguments. As you can see, one has to go through the definition of the extension principle. By the way, I have updated this old paper of mine with new references, and if you like, I can share it with you after the conference so you can follow these arguments. Okay, so there is a little remark which I need to make because, of course, the interest is not on having the fuzzy parameter again as a variable in the solution. The interest is on U, so we can project the solution onto the first variable. This is the projection operator pi, which I will need soon. The problem is that we need this prolongation because if we don't take the prolongation of the system, this will not be a solution. Right? Okay, for reasons which are well known to people in fuzzy sets. Okay, so now the next step is how can we embed generalized functions as fuzzy functions? Well, the idea is rather simple-minded. For example, if we have an L-infinity function, we can view it as a fuzzy continuous function. Well, of course, we mollify as usual. I don't have to explain this in the community. And then we can define a fuzzy continuous function U0 through the membership function, where it gets the value 1 minus alpha if V is one of those regularizations at level alpha and otherwise 0. Okay, so it is a very simple assignment. And then one can easily prove that this is an embedding. So L-infinity is contained in the fuzzy continuous functions. And okay, I will not read the proof. And of course, we can extend it to integrable measures if we want to stay in the fuzzy bounded continuous functions in the same way. Okay, so we have now embedded some non-smooth functions into the fuzzy bounded continuous functions. Okay, so then we can say the following. If we have initial data in M1R and if we have a fuzzy constant, then we can embed this initial data. Then we have embedded initial function and the parameter lambda 0. And then we can solve the equation and get a fuzzy solution, which is a fuzzy function in this function space. Okay, so one can solve the Burger's equation with generalized initial data and fuzzy parameters if one likes. One can also keep the parameter crisp and gets a fuzzy function. Okay, but we can say more, right? What is the relation of this fuzzy solution to the weak solutions? Well, of course, it is well known if we have the Burger's equation with viscosity and we let the constant tend to 0, then in the limit we get the solution of the inviscid Burger's equation, but a weak solution, because we have in general shock and rarefaction waves, etc. Well, this is Hopf's paper from 1953, I think. And a weak solution means that we have here the equation satisfied when integrating against the test function. Okay, so we have a weak solution with such initial data, and then the question is, can we put this in the fuzzy context? Well, the key idea is to introduce the notion of a fuzzy zero. A fuzzy zero you can see here, I hope. Well, it's just a triangular function around 0. At top is 1, and the intervals here are shrinking to 0 as alpha goes to 1. Okay, that's all which is required of a fuzzy zero. And okay, now we need also to extend the weak solution concept. So we, for each test function phi, we can have the inviscid solution operator, which should be 0, right? And then we can extend it to the fuzzy sets, fuzzy functions. Right? And then we can say that an element of this space of fuzzy function is a fuzzy weak solution if the extended weak solution operator gives a fuzzy 0 for every test function. Okay, and then indeed one can say this if the lambda was a fuzzy 0, positive of course, then if we construct the fuzzy solution, say for L infinity data, then this W, which is the first component, the U, the original U in the equation, is a fuzzy weak solution of the inviscid Burger's equation. Okay, so I said what it takes, a little bit of classical analysis and entangling the soups in, say, 5 to 7 different lines. Okay, so the final thing is that one can also play the game of association, right? The question is, okay, now I have just shown that the fuzzy solution constructed actually is a fuzzy solution of the inviscid equation if lambda is a fuzzy 0, positive fuzzy 0. Okay, so then the question is, can one relate this fuzzy weak solution to the classical weak solution? And of course, we can look at this integral here, which is a semi-norm on the space of bounded C-infinity functions, for example, or bounded functions. And then we can extend it onto the fuzzification of those functions. And then one can say that two members are associated if the difference is a fuzzy 0, just as in Colombo theory. So I even mentioned the word Colombo, right? So here we have a phi epsilon, it tends to 0, and here we just say it's a fuzzy 0. Okay, and then of course one has also an embedding of the L infinity functions in R2, to which the weak solution belongs, and then one can say nicely that if the L infinity data, we have initial data L infinity, the solution, entropy solution, and we have also the fuzzy solution with the fuzzy lambda, then the two are associated. Okay, so this needs a little bit more of machinery, which I cannot present right here because I'm running out of time and I'm coming to my last slide. So the interesting thing which makes all work is this factoriality of the extension principle. So you can extend all operators and then one has a meaning of the extended equation in the fuzzy realm just as the underlying classical equation. Okay, so in this framework, differential equations with fuzzy data and fuzzy parameters have unique solutions. One can view some generalized functions at least as fuzzy functions. And so the concept of weak solutions can be replaced by fuzzy sets theory, because as you see in fuzzy sets, we don't need weak solutions. All solutions on the underlying space are classical solutions. They are just fuzzified. Okay, so I hope that I have indicating that this approach could have the potential for a general theory. And with this, it's 10:40, and I'm also through with my presentation. Thank you. Okay. Thank you. So how do I get back to the... here I am. Okay.
Oh, thank you. As usual, Michael gave a lecture which should be a starting point for some young mathematician. It's really something new, foundation again. So we will see. So do you have any question? We can get question through chat. Probably we are shocked with the lecture and then it's difficult to ask questions in this moment, but for the future this will be interesting theme for other people. So Michael, thank you very much for your nice lecture.
Well, thank you. It was my pleasure. I'm looking forward to the next lectures.
Yes, now we go to another great mathematician, friend and colleague, Hans Heitinger, who are also founder of a field of time frequency analysis. Actually, he invented modulation spaces, and modulation spaces are the basic framework for the differential calculus at modern mathematics now. Okay, he will speak. He can speak about everything. Whatever you ask him, he will answer you and give you more questions again. But today his lecture is this with Hermit functions and computational aspects of fractional Fourier transform. So Hans, do you hear me?
Yes, I can hear you, and I hope you all can hear me as well.
Yes, everything is perfect. So
very good.
I will sit here. Let me tell before something more. Many of our colleagues from Novi Sad, they follow this conference somewhere at our faculty, actually. So in this moment, I would like to invite them at 1 o'clock. We will have a nice buffet down in the rectorate, and so they can join us, who is here in Novi Sad. Of course, sorry for you who are part of Novi Sad in this moment. So please,
I hope that meanwhile you can see the slides.
No, not yet.
Okay.
Not yet.
Because I put share screen.
Try again.
Yeah.
Okay.
It's okay.
It's okay. It's fine.
Okay. Now it works, yeah? Okay. So thank you for the possibility of presenting some ideas, actually kind of presenting a picture book. I will not use many formulas today. And also I must say that my original plan was to follow my talk, a presentation by Maurice de Gausson, Unfortunately, he couldn't make it, and actually at the moment he is back to the hospital, so we wish him all the best. So his talk would have been on the metaplectic group, and the metaplectic group contains as a subgroup the fractional Fourier transform. So by kind of terminology, I'm trying to do something fractional in time frequency analysis. The fractional Fourier transform has not too much to do, at least until now, with the fractional calculus that we have heard before. But I think I can give you an idea what it is about and what my computational viewpoint is on this issue. So I would like to remind you that the basic tool in time frequency analysis is the short time Fourier transform. And the short time Fourier transform has the nice property that rotation corresponds, the Fourier transform corresponds to rotation. So usually we call the short time Fourier transform Vg of f. G is the window and f is the signal. So if you have a time signal f and you take a Gauss function which is invariant under the Fourier transform, then you observe that at least in absolute values, the phase factors don't play a role, they're harmless. You get a rotation. And so you could have the idea, okay, maybe the rotation by an arbitrary angle is something which is a fractional Fourier transform. If you look at the spectrogram of a pure frequency, the musician would say that she or he is hearing a pure sound at a certain frequency. So it's something like constant tone, and we all know that the pure frequency under the Fourier transform gives you a Dirac, which is a vertical thing containing all the frequencies. So a fractional Fourier transform of a pure frequency should be a so-called chirp signal or a frequency sweep, which would be something like, and if I would have P.Balazs STX program here, I would show you, you would see the line that corresponds to the frequency as a function of time. Okay, so this is the idea. And of course, the Fourier transform should correspond to rotation by 90 degrees. And the idea, or the quick explanation is, well, we all know that the Hermit system is an orthonormal basis for L2, so for the Hilbert space setting. And the eigenvectors are powers of the unit roots of order 4. So the standard way of normalizing things is to start with 0. So the Gauss function is the Hermit function number 0. And then you go with the index and you have eigenvalues minus I, minus 1, plus I, and plus 1. And so kind of surprising to many people studying Fourier transform, a quarter of the Hilbert space is Fourier invariant, and you have 4 other eigenspaces. And so the idea of the fractional Fourier transform can be described. You can embed this torus group of rotations into the metaplectic group, and I have to skip this. I just show you a few of these references. Now, what I observed, especially in discussion with Kurt Bernardo Wolf, he is a person in optics, where fractional Fourier transforms appear quite often. There seems to be a stream of papers going back to Namias and Almeida in the late 70s, early 80s. And the people in quantum mechanics and in optics joined the forces, but they overlooked that André Weil already had this famous paper in '64 on the metaplectic group. My advisor Hans Reiter was trying to illuminate it and give detailed proofs. So this is something that I think will be we will see a lot in the future. Now, the simple picture that I do with my MATLAB program is take a bandpass signal, so some smooth function with some maximal frequency. You see it here. If you apply the Fourier transform, you get something which is the same pattern, but in a vertical position. And I will later show you pictures of how this looks in the discrete setting. Now, going straight to the discrete Hermit functions, there are many possibilities. You can take the continuous Hermit functions and sample them then you get a non-orthonormal system because the orthonormality of the two integrals is lost. So you can try to say, well, they are eigenvectors for some operators, and you discretize the operators or so. And this is more or less the idea that I had. And I show you quickly my program of computing the Hermit function, which I think I did about maybe 10 years ago during an Oberwolfach conference. I decided, oh, I have all the tools to do it, and it actually works very, very nicely. So if you give me a number n and you would like to compute an orthonormal basis for signals of length n, then I would say I have to create a Gabor multiplier or STFT multiplier, or some people call it an Antivik operator, which is written in the third line, a Gabor multiplier with a symbol. And the symbol is a weight, and I have also a window, and one just says that this is a full, not sampled, it's not a Gabor multiplier, it's a full symbol. Now first I show you the profile that I'm choosing. It's just more or less any radial symmetric weight function. So in the famous paper of Ingrid Dobschi on localization operators, you find that Hermit functions are indicator functions of the operators which take the function, take the short-term Fourier transform, multiply with a radial symmetric circular profile and go back. And you can imagine a radial symmetric function is a limit of partial sums of such things, so they are better in this sense. And what I'm doing is I'm taking the short-term Fourier transform with a Gaussian window, then I multiply with this profile, and then I go back, and then I do eigenvalues. And if you say, well, if somebody is trying to multiply in phase space with this, where is the location for the biggest eigenvalue? And you will say, well, it's something which in phase space tries to be maximal concentrated here, which turns out to be the Gauss function. The Gauss function in the discrete setting is a periodized sampled version of the continuous Gauss function, and everything works fine. Now the second guy has to be orthogonal. In the phase space picture, orthogonality means it has to be located at a slightly different place. So if you try to stay near the center but orthogonal to the first one, you find yourself in a circle around it, and so on and so on. So if I show you the time frequency pictures of these orthonormal systems, they will be perfectly circular, at least up to the point where they are touching the boundaries, where periodicity comes in. And if I show you the plots, you see these functions, which look very much like also other functions, because I can only show you the low numbers, so number 0, number 1, and so maybe this is the better presentation. So this is the Gauss function invariant on the Fourier transform number 0, 1, 2, 3. Number 4 is again a symmetric real-valued function with the Fourier transform, and it's up to normalization invariant on the Fourier transform. Now, once I have with my MATLAB routine such a thing, you have to observe that it was not exactly the Gauss function. So the rest is just telling you, well, sometimes an eigenvector routine may give you the negative value or something else. So you have to first go to a real valued thing because it's a complex valued function at the first time. And once you have it real valued, maybe it's still the negative of what you have usually. And so these 4 lines are just making the same pattern. And if you look at these Gauss functions, you can say, well, you try to make the right branch positive, or you make the integral on the left and right bigger, and then you find yourself at something which is like the continuous Gauss functions. Now, applying the fractional Fourier transform in the discrete way to this, I have to tell you what it is. The fractional Fourier transform makes use of the fact, going back here, that when you do the full rotation, you have I. And as we know, I in the complex plane is 90 degrees. So if you ask me what is the fractional Fourier transform which corresponds to the square root of the Fourier transform, just put 45 degrees. So cosine of 45 degrees plus I times sine 40 degrees. So essentially, the fractional Fourier transform is a diagonal operator where instead of putting these powers of unit roots of order 4, you put an arbitrary or an appropriate pure frequency. And we know what pure frequencies are in the discrete setting. So in this way, I'm getting these pictures, which can be used also to have Gaussians, which are now not only horizontal and vertical by taking squares or so, but going in arbitrary directions and have a elliptic shape more or less in this direction. Now I'm telling you that there are already in the LTFA toolbox, which you can get other functions, where if you go to the higher numbers, they're trying to smooth out the square here, whereas I'm having functions which are more circular. And if you apply these things to chirp signals, so chirp signals are these pure linear frequency sweeps, then the right version is the way that I'm getting, whereas the LTFA toolbox does some distortion of this. So I'm showing you another one. So of course, everybody knows that we cannot really rotate a discrete picture, but the part which is in the interior is rotated in an almost perfect way. Maybe I skip this. If you want to know what happens if you do the fractional Fourier transform of a rectangular function, you see at the very end the sinc function in the discrete version. And whereas concentration is lost as you go through all these things, smoothness is increased. So this is discontinuous, but very concentrated. The sinc function is very smooth, but discontinuous, but not very well concentrated. And you could show how this is moving around in phase space. Also, the comparison of the two methods in the LTFA toolbox and the approach that I have is maybe up to the number n1/2. I'm working with signal length 480. You get very similar results, practically the same, but at the boundaries you get something better. I'll skip this. And if you are asking in which sense this is better, I would like to recall that the transition from the I would like to take the perspective that the discrete signals are not just for a fixed n, but you should look at them as representatives of something continuous with variable resolution. So I would like to share some ideas in this direction with you. How can I get to the discrete Gauss function? Well, I take the Gauss function, I periodize it, or I sample it, or I do both of them. And of course, if you do it in a compatible way, you get a discrete periodized way. Now I'm to check, yeah. This is a picture where you see this continuous function. And it's very important to do this transition into the finite domain in the proper way. So where does a periodic function start? And you would say, well, you cannot say. The green picture tells you this is a nice plot, but the red picture tells you this is the group theoretically nice interpretation, and that's the one that you should throw into MATLAB, because you are starting to represent it from 0 to n-1. So the plot is not good, but the Gauss function taken in this discrete way is the right one, and you need a separate plotting routine that shows the Gauss function, the discrete Gauss function in the right way. So in this way, I would like to make a comparison with different approximations in the domain of numbers. So we all know, well, a real number is just a limit of Cauchy sequences of whatever numbers you take, rational numbers, for example. But if I'm asking you whether 53/17 or 41/13 is a better approximation, you have to compute the numbers, and they're not well organized or so. It's much more beautiful if you take decimal expressions. If you take more decimals, then you have a better approximation, obviously. So what is the analog if you're doing it with functions? So if I say, well, the number n are disorganized numbers. If you take n to be a square number, maybe you can say, well, I take, let's say n is 144. I would say, okay, maybe you think of the period is 12 and the sampling rate is 1/12. But if you want to have now a sequence of numbers, the best way of doing it is to go to understand how the kind of the adding of one more decimal term that's multiplying by 4. So I give you the example, if n is 1024, or you can say it's 32 squared. So if the original period was 32 and the sampling rate is 31 over 32, how can you go to the next level? And you just multiply by 4. You double the period and you double the sampling rate. And now you have 4 times as many samples, but the good thing is if you start at 0, every second sample, as long as you're in the first quarter of your sampling, of your fine sampling, should correspond to a sample from the old version. Then you have the enlargement interval to the right, and you have the enlargement interval to the right, left, which are not existent in the coarse sample. And then again, every second sample is here. So there's a very clear recipe of how to compare not arbitrary discrete numbers, but numbers which are differing by a factor of 4 only. And so when I do my discrete Gauss function, Hermit functions, so these functions, I go back, these functions, and I do it for n 1024, n 4096, and I compute the error. I find that this is really very nice and working very well, which gives me the hope that eventually we will be able to prove that in the norm of the Banach-Gelfand triple, so now I'm jumping to the end, you know, I like to use the Siegel algebra is 0, or the test space or modulation space M1, because this is really the analog of Vindas absolutely convergent Siegel algebra of absolutely convergent series in the context of Gabor analysis. So in this setting, Norbert Kaiblinger was showing that if you sample a function in the space of test functions, you take the FFT, so the discrete version of the Fourier transform, and then you go back by piecewise linear interpolation, quasi-interpolation by cubic splines or so, you're getting a very good approximation. And now I'm hoping that with this discrete version of the Hermit function, obtained by a discrete analog of the eigenvalue routine, you should be able to get a discrete verification of the continuous fractional Fourier transform. So what I have shown you was based on a discrete rectangular function, but I think it imitates the true behavior very well. But there is a lot of things that we have to do. And I just want to give you at the very end a few references. So if you want to read about the metaplectic group, the papers of, or the book of Maurice de Gosson, where he already observes that the invariance properties of this Siegel algebra is 0 is quite helpful. You find details also about metaplectic groups in the book of Gröchenig, or properties of S0 in the recent work of Mats Jakobsen. At the end, because it was mentioned the Tauberian theorem, I would like to promote at least a little bit an old and almost unpublished paper. It was a very difficult to access proceedings volume, which I did on the Tauberian theorem related to what is called the third Wiener-Tauberian theorem. And it's about functions of bounded quadratic means. So if you look up in the book of Wiener, you find the usual that Nenad was mentioning, the L1, L infinity version. The second version is with what we also call Venus algebra, with the amalgam space local C0 global L1. You can say this is the situation where you take a smaller test function or algebra, which is related to Riemann integrals. The dual space is slightly larger, the space of translation bounded Radon measures. And this third approach was done in a fairly different way, I would say already in the spirit of distribution theory and distributional Fourier transform before they were born and well described by Bochner and Laura Schwarz. Whereas I was finding that you can use quite elementary, in a way, elementary decomposition methods to generalize these results for general parameter P, not just P equal 2, to multidimensional, and this is described in this paper. So I would like to thank you for your attention, and I'm free for questions. Thank you very much.
It was nice to hear you. Nice lecture. Now I'm on. Okay. So first of all, P.Balazs sent a message that maybe you should make a small smile when you talk, but we will make you smiling because we would like to congratulate your birthday today, Hans.
Okay, thank you very much.
It's really great news. All the best, Hans. Nice to hear. Some of our colleagues just informed us that this is today, so great thing. I would like to ask you something. Okay, so this is fractional Fourier transform, and then you have spectrogram, which is different, and so rotation, as you presented this, with the metaplectic transformations, which are probably done by Gosson in this whole group of metaplectic transformation. My question is related how one can use technically, because when we have Fourier transform, we develop to differential calculus, everything by Fourier transform. How much I saw some results with fractional Fourier transform, but how much it can be involved in the theoretical aspects of Fourier analysis?
Well, my understanding is, and I've been collecting literature in this subject, and it's a fairly big subject where not too many mathematicians are active. So it's actually much more in, I don't see the applications in the area of differential equations or pseudo differential operators or so, but much more in the connections to physics and optics. So somehow the idea is that if you're asking what is in the focal plane, then you get the Fourier transform. And then you're asking what is if you're in between, and then you have the fractional Fourier transform. So I'm quite optimistic that if people are doing optical communication and that the simulation of signal processing problems using fractional Fourier transform should be quite relevant, but I cannot give you a very detailed answer at the moment. So yeah, so it's more in, my expectation. It's much more in the applications. And one can say that there is also a theory where people say do we have a convolution theorem? But the convolution goes into pointwise multiplication if you rotate by 90 degrees. But of course, you can define a fractional convolution, which seems to be interesting to some people. If you go to the fractional Fourier domain, multiply and go back, you can define fractionally band-limited functions. You can have sampling problems. So there's a lot of literature in this thing replacing ordinary Fourier transform by fractional, or also uncertainty principles related to the fractional multi-dimensional cases. So I think there's a lot of things going on also in the mathematical literature in the last few years.
Thank you. Let me mention the name of Ahmed Zayed.
Of course, I was about to talk about. I mentioned his name. Yes, of course.
Yes, he's a man of our generation, and he does such things.
Yeah,
yes.
There are different versions of multi-dimensional Hermit functions, and I should mention metaplectic group contains not only rotations but of course also shears. And somehow, for me, that the use of metaplectic group should be like going from Gabor, which is for me like step functions, to piecewise linear functions, which is a kind of differential geometry within time frequency analysis. So if you have a chirp signal which is going up and down, you wouldn't like to approximate the spectrogram with piecewise constant pieces, but you would like to follow that. And for this, I need the metaplectic group. Yeah.
Okay. So thank you very much, Hans, for a nice lecture. Now we will have a break, and we will start at 11:30. according to our schedule. So thank you very much for the taking part in this morning section. Da.
I cannot hear.
Yes, because the professor will announce you.
Yeah, it's just 1 minute. So
Okay.
let us resume after coffee break. And our second morning session comprises 4 talks, and I'm very happy to announce our next speaker, P.Balazs from Acoustic Research Institute in Vienna. So Peter, please use your time to tell us something about kernel theorems in Coorbit theory. Thank you very much. Okay.
What I wanted to show first is what.
So now is your time.
Yes, I know. Good. Does it work? No, let him not. Okay, then let's stop. There's some problem. Okay, so I thought a bit, what can I present that is connected to time frequency and also to distribution theory. Can you hear me?
Yes.
Cool. Very good.
So everything is fine. Yeah.
Good. Okay, so I thought, okay, I will talk a bit about kernel theorems and how they're connected, well, to frame theory and stuff like that, and time frequency. And I had some major fight with Beamer and LaTeX, so let's see how it works. So I didn't sleep a lot this night, but okay. So this is joint work with Karl-Heinz Gröchenig and Michael Speckbacher. So what is the basic background? So what are kernel theorems? Kernel theorems are results that say good operators can be written as nice integral operators in some way. So there is this famous Schwarz kernel theorem, where it stated that an operator maps the Schwarz functions into the temperature distribution in a bounded way if there exists a unique kernel, which is a temper distribution with the double dimension. And the duality relation is like you see here. You probably see my mouse. So, okay. There are several other distribution spaces possible to formulate kernel theorems like Gelfand-Schilov spaces and others. Hans has developed some kernel theorems for the modulation spaces. We will talk about this later, what the modulation spaces, but those are spaces which have nice short-term Fourier transformation coefficients. And the advantage for those that don't, well, the advantage there is that you can deal with Banach spaces. And so if you like norms, this is what you want to do. And if you want to associate it to proper integral operators, you can apply Schur's test. And what we did is we generalized it to, well, general Coorbit spaces. So Coorbit spaces on more general transforms. And for that, we use group representations. So we start out with a locally compact group with left H measure. Sorry. Where a unitary representation from this group into the unitary operators on a separable Hilbert space H. We assume that pi is square integrable and irreducible. And any psi which fulfills this inequality is called this, which is where the how should I call it? Well, that's where this integral is bounded, is finite, is called admissible. Then there exists an operator which is densely defined and which fulfills the lower equality. So you could say, well, we need, okay. So the inner product of the representation using this representation. The inner product of coefficients using these representations is just given by the inner product of the signals and, if you so want, the windows. What did I mean with that is, so you can define a generalized wavelet transform in this way. So you take an admissible function and apply the representation on it, go through all the elements of the group, and then you get this generalized wavelet transform. And if we assume that the norm of T psi is 1, then we get an isometry. The adjoint of this transform is given by, in a very canonical form, by this. So you take an element in L2 of G, and you multiply it by the, if you want, group shift. So if you multiply it by the representation of G applied on this element and take the integral, then this is the adjoint operator. So if you want the synthesis operator, in this setting, we get that it's V star times V is the identity. So if you want, with other words, this is a continuous Parseval frame. So you get the representation by this formula. You get a representation of every element in the Hilbert space by this formula. And so what is Coorbit theory? Coorbit theory is, you can describe nice functions by nice generalized wavelet transform coefficients. And to measure what nice is, by the way, I keep on looking on this side, but because there is my screen, but yeah, it would be, yeah. As if I would be in your room, I would look back. Okay, so so how can you measure what is nice? How can you, and for this, we use LP spaces, weighted LP spaces. Let's have 3 elements, G1, G2, G3 in a group, and let's have several weights. So W should be submultiplicative, M should be W moderate. Let's forget the technical reasons for that for now, but this is the assumptions. And let's assume that pi is integrable with respect to W, which means that there exists an admissible psi such that the generalized wavelet transform of psi with itself is in the weighted L1 space. So this one. And it's not 0, of course. If this is fulfilled, we can define the test function spaces. So the nicest space of functions, or the space of the nicest functions, which is H1W, which are those functions in the Hilbert space where the generalized wavelet transform is in weighted L1. We can look at the its antidual and to get the distribution space. So where we just look at the antidual of HW1. And we see that the inner product extends to this dual spaces. So if you want, the duality can be given by the inner product on H. So H is something like the pivot space for this duality. And then we can define the Coorbit spaces. So the Coorbit regarding with this representation of LPM are just those distributions or those F in the antidual of H1W, where the generalized wavelet transform is in the weighted LP space. And the norm is just the norm of the transform in, so the norm of the F in the Coorbit space is just the norm of the transform in the weighted LP space. Okay. What we see and what can be shown is that the Coorbit spaces are just Banach spaces. The Coorbit spaces corresponding to L2 is just the Hilbert space. All the Coorbit spaces are between the nice space H1W and the distribution space, which we denote by H1 divided by omega infinity. The Coorbit space connected to the weighted L1 is just H1 with the weight. The Coorbit space related to L infinity with the reciprocal weight is exactly this anti-dual. So the distribution space, if you want. Okay, what are properties of those Coorbit spaces? So let psi be an admissible element with regards to the weight. Then the generalized wavelet transform is an isometry between the Coorbit spaces of weighted LP into weighted LP. The adjoint of this is continuous for all P. And for all those Coorbit spaces and all those weighted LP spaces, the adjoint composed with the original transform is the identity. So again, if you want, this is in this case something like a Parseval Banach space, continuous Parseval frame. Okay, so if we have an element in the weighted LP space, we can say by the correspondence principle that there exists an element in the Coorbit spaces such that it is mapped to this big F, if and only if big F is equal to F convolved with V psi psi. So this is some kind of reproducible kernel, well, reproducing kernel property. There's a duality relation. So if we choose a P between 1 and infinity and 1, then the Coorbit spaces of LP, of weighted LP space, is just at the adjoint of the Coorbit space for the weighted LP space is just the Coorbit space where you just take Q. So it's the Coorbit space of the LQ space with the reciprocal weight, and 1 divided by P, 1 divided by P plus 1 divided by Q is 1. And there's some discretization scheme. So there exists some a sequence in a group and some coefficients from the Coorbit spaces into the complex numbers, such that you have a representation of F with these coefficients and the how should we say, and with the atoms you get by this representation where these coefficients are bounded. So the weighted L1 norm of those coefficients are bounded. Okay, so we now go towards tensor product. So most of you know, so what a simple tensor is just a formal product of two elements in a Hilbert space, for example, which fulfills the homogeneity property. So, well, this one. So it's so alpha, yeah, alpha. So if you multiply by a scalar, this is the same as multiplication of the first term or the second term or of the result. And we can define a tensor space by and we define this tensor space H tensor H by the closed span of those simple tensors. So we just take the elements of the space and create the, let's say, free tensor product or the simple tensor product, and then look at the span of them completion with respect to the end product we get, where we use the inner product on the simple tensors, just which is just defined as the multiplication of the inner product of the terms in these tensors. Okay, sometimes these tensors said or are considered to be the Hilbert-Schmidt operators. Well, this is in some sense true, but this already involves implicitly a non-trivial kernel theorem. So we would like to distinguish Hilbert-Schmidt operators and tensor products where possible. Okay, So in principle, we now have two groups, two representation, two Hilbert spaces, two admissible wavelets or generalized wavelets, a lot of weights. Question is, can we now create the representation for the tensor products? And yes, we can. So we can now very simply define a representation on the product of G times G just by defining the representation, or tensor representation of G times H is just the tensor of PH tensor PG, and where this new representation acts on a simple tensor just by this. So very simple. So the representation with GH is just you take the representation using H applied on phi, and then take the tensor of the representation of G and apply it on psi. This is again, if you started with unitary representations, this is again unitary representation now of G times G on H tensor H. Also, if we started with irreducible representations, this is again irreducible. And in those cases where we would like to link those tensor products with the Hilbert-Schmidt operators, these representation acts in this way. You can say in a way how you can define tensor product operators. So you take so P tensor of G and H applied on A is just P of H, pi of H, sorry, times A times the adjoint of pi of G. Okay, what's the time? Yeah, I have to speed up, right? Good. So if we have two elements, so we now take an element in the Hilbert space, we can now define an element in the tensor of this Hilbert space just by taking the tensor of this psi. So big psi is psi tensor psi, which is of course in the tensor product of the Hilbert space. Now we can define a tensor wavelet or generalized tensor wavelet transform just in this way. So V psi of the tensor at GH is just you take the generalized wavelet transform of F2 with the psi, and then the generalized wavelet at the position H, and then the generalized wavelet transform. Oh, what happened now? This one. And then take the generalized wavelet transform with psi of F1. Okay, let's leave out the technical details. What we can say is, if we do it like this, again, the Coorbit spaces for this new representation is well defined. So they are well defined. So we can do more or less the same theory on the tensor product as on the Hilbert space like. And so, if we have now an operator from the Coorbit space of L1 into the Coorbit space of L infinity, I will not mention the weights currently. So an operator that goes from the test function to the distribution spaces. The goal is how can we associate an integral operator to this operator, A. And the formal calculation is, okay, we know we have the generalized wavelet transform, which is an isometry, and we get the representation formula. So we have this formula. We can apply the operator A to get this formula. And then we can, on this, we can just apply the generalized wavelet transform to get this formula. And what we say here is, okay, we have something like this, which is a representation or a kernel representation of the operator. Where, yes, this is a continuous Galerkin-like representation, if you want, of A, where you can represent the, yeah, because V psi is invertible, this is a representation of A. And we can now define the, I think it's a calligraphic A by this. So we take this, how can, let's say, let's call it Galerkin representation, and multiply it by Fg for an F, and take the integral. Then we see that, yes, so if we take the generalized wavelet transform of the A, this is the calligraphic A of V psi, if and only if A is like you see above here. If A is the adjoint of V psi applied on the calligraphic A applied on V of psi. And Coorbit theory allows to make this manipulation precise. Okay. Good. So let's talk about the theorem now. So if we start out with an integrable representation of G, then we can see that an element in the Coorbit space of L infinity defines an operator from the Coorbit spaces of L1 into L infinity, where this duality relation is fulfilled. And the operator norm of this A is just the Coorbit space norm of this K. And on the other hand, if we have an operator on these Coorbit spaces from L1 to L infinity, and it's bounded there, then there exists a unique kernel in the Coorbit spaces. Okay, I think I'm nearly done, Nenad, right?
Yes, this is.
So let's now. You can do it with P. Okay, so you don't have to. You can do it for operators. Oh wait, so this one. You can do it with operators from Coorbit L1 into Coorbit LP, and from operators from Coorbit LP into Coorbit L infinity. Okay. Examples. Too long. Sorry. Maybe as an outlook, what I think, I'm quite sure. So Codero and Nicola visited the Feichinger's kernel theorem recently, and they said in some sense they stated that this reveals the superiority in some respects of the modulation space formalism upon distribution theory. In this paper, we added a more abstract point of view and argued that the deeper reason for this would be the Coorbit theory of Coorbit spaces. And we've shown it for representation. And I think, and I'm quite sure, and it's just has to be done. I think that the group structure is not possible. You can do it for example, localized frames where can still define Coorbit spaces, and all this theory still makes sense. Okay, that's it. Thank you. Sorry for the too long talk. As I said, I had a fight with Beamer this night.
Okay. Okay. So thank you, Peter. So my assistants don't give me any questions for your lecture, but anyway, we should. Yes, Professor Filipovic has a question.
Thank you very much for your nice lecture. I would like to ask you. Now it's a hot topic. All what you told, it's very interesting for other people. For example, we consider so-called modulation, translation in various spaces, and then come to similar things and some new spaces, even we do this in this time, just in this time. My question is, if you take for G, Rn, just a Euclidean space, then you arrive to classical theory, to short factory transformers and all other things. Is it true, or how you can you get some new results in that frame? I mean, not frame theory, but in the framework of Euclidean theory, global theory. How it looks like.
I had some problems understanding the question. Maybe Nenad can repeat the main components.
Okay, so the thing is that if you put, for example, Euclidean group R to dimension D or something like that, do you recover known results? So do you gain something new? This is the one thing. And another thing is, okay, so the generality with respect to other groups, did you have some concrete examples?
Sure. So I think, as far as I remember, for the modulation spaces, everything was more or less done. So there we just could recover it by the more general approach. We could do some new results for Bessel spaces. And what is interesting, we can we can combine all the groups you can think of. So you can choose a nice group, the group you like for the one side, and choose another one for the other side. We can still do it. So if we separate G, so G, and if we don't have the same G, but use G1 or G2, you can talk about what are the, how can you formulate kernel theorems for operators that map a certain modulation space to a certain Bessel space, for example.
Oh, okay. I see. I see. Okay. So,
did you consider different kind of topologies? But if you make tensor products, do you consider this is what I see? This is P tensor product. P.
Yes. We have used, as far as I remember, the productive. No, that's not productive. The projective, right?
Yes. Yeah.
Topology. You could also use others. Of course, if you use the one topology that is induced by the Hilbert-Schmidt, by the Hilbert inner product, you get well. This is really similar, very similar to the topology. Is very similar to the Hilbert-Schmidt operator topology. So you again get the Hilbert space and all the stuff. Did I answer the question or not?
Yes. Okay. So thank you. So we are immediately going to the next lecture. From here, we have our guest, Professor Ville Turunen. He is in Novi Sad, and he will present his lecture about time frequency analysis on locally compact groups. So it somehow suits well. So Ville, please.
Thank you. Thank you. So let's see. There. Okay. Thank you very much. This talk is now dedicated to the memory of Professor Bessel. I'm going to talk about time frequency analysis also on locally compact groups. I have to restrict a little bit of which kind of local compact groups I'm talking about. Part of the results are also new for Euclidean spaces. And you can always think about these results that I'm going to present, that how do they look like on Euclidean space, ordinary Fourier analysis there. So my aim is to generalize Cohen plus time frequency analysis on two differential operators to one classes of groups. And let's see, so I do have some visualizations of ordinary time frequency analysis, like here, there is some one-dimensional sound signal, human speech, and then I have infinitely many different ways of presenting the same signal as different time frequency distributions. These are like musical sketches, musical notation of that given signal. So here, for example, is so-called discrete version of Jordan time frequency distribution for that speech signal which was given here. Here is discrete version of Wigner distribution. And typically on Euclidean spaces, people start with Wigner distribution and take some convolution smoothings of this. Usually, Wigner distribution is otherwise mathematically nice, but it's very sensitive to noise. And all those signal manipulations that we're doing with pseudo-differential operators, they are basically seeing those time frequency distributions of signals. And if the time frequency distribution is somehow unclear, also it's very difficult to have reasonable processing of the signals that way in practice. So I'm then a little bit convolution smoothing that Wigner, for example, and getting Born-Jordan distribution, which has much more clarity. It's like showing horizontal lines which are whistling sounds and vertical lines which are snapping sounds. And in this specific case, this is invertible distribution, so no information is lost about the signal. But if you do too much smoothing, like here in a windowed Fourier transform or short-term Fourier transform, and you take the corresponding spectrogram, the energy distribution, then you're smoothing too much, and it's like melted away with the information. You cannot anymore recover back the original signal from such a picture. And that's also then causing difficulties for manipulating these signals, for example, removing noise and so on. Okay, here's another spectrogram, here's another spectrogram. And now I want to somehow describe how to generalize density groups. Can we learn something new about Euclidean spaces also that way? You're going to see some pictures at the end of the talk related to that. So just as a reminder, usually the Cohen class time frequency transforms are convolution smoothings of Wigner transform. I'm going to present the formula for Wigner transform soon. And once you fix your favorite time frequency transform, you're basically choosing one convolution smoothing at a time. And then you get corresponding pseudo-differential operators, which are given by those formulas 2 and 3 on these slides. And we like to now investigate the properties of those time frequency transforms and pseudo-differential operators on groups. Here, the Euclidean version of Wigner transform in formula 4. This corresponds to Weil quantization of pseudo-differential operators, which is given in number 5. And what is now the bad thing if you try to use this Wigner-Weil approach on the groups? In general, you cannot have that division by 2. You see in formulas 4 and 5, there is division by 2. And that's like really poisonous kind of thing on many groups. You don't have that sort of taking division by 2 or in multiplicative notation, you cannot take square roots. That's really difficult. Already on circle group, you realize this question. But there is another way around of this thing. Namely, we can rewrite also the Euclidean theory centered not around Wigner, but around Cohen-Nirenberg transform, Cohen-Nirenberg quantization. And you see Cohen-Nirenberg pseudo-differential operator formula at the last row of this slide on Euclidean spaces. And it's corresponding to so-called Riesz time frequency transform, which is that second to last formula on this slide. This can be easily generalized to groups. So we start doing that. We have to restrict a little bit on which kind of local compact groups we can work on. We need to have decent enough Fourier transform. So we are going to capture all commutative locally compact groups. They are in some sense, let's say, technically easy. A little bit more we can do. We can have so-called type 1 unimodular second countable locally compact groups. They don't need to be any more commutative. They include all the compact groups. They include Heisenberg's groups, etc., etc. Plenty of non-compact, non-competitive groups can be captured. And we're having, of course, a nice harnesser on such groups. And then there is some sort of like plunger and measure. Measure is not the exact word now. We have to understand this, those integral formulas in a little bit wider sense, but now we're not going to details of representation theory. In any sense, we're having unitary Fourier transform, which is taking our M2 functions on the group to some sort of M2 functions on the unitary dual, like in Euclidean space. So I'm then marking that I'm having Fourier transform calligraphic F for this hat. U hat is Fourier transform of signal of U. And initially U is just some nice enough function, complex value function of the group. But now in non-commutative group case, those Fourier coefficients are some operators acting on Hilbert space. Don't mind now about the details. Those eta y things there, their eta is like frequency. But eta 1 is certain operator acting on Hilbert space. You can think about that in Euclidean Fourier analysis, it's complex exponential function. You have those e to I to pi x eta or whatever. That's the sort of eta thing there. Inverse Fourier transform is also marked by integral. It's usually non-commutative setting, not usually integral. It's some sort of like integral or sum of weighted traces of operators in Hilbert spaces. Again, don't mind the details. Then, with this Fourier transform, we can have symplectic Fourier transform, taking L2 functions on so-called time frequency plane, G Cartesian product G hat to some sort of like ambiguity plane functions. Important thing to remember, when dealing with non-commutative groups, then those eta integrals, the pre-Keplerian integrals, they are not anymore like integrations of ordinary complex value functions. They are some sort of trace formulas in Hilbert spaces, and then you cannot change easily the order of integers. You cannot like AB, BA, maybe there is no commutativity of operators, so you have to be careful, like mentioned in the last line of this slide. Okay, so then we can neatly generalize coherent transform to the also to these non-commutative groups. So formula 6 here is the equivalent of Riesz or coherent time frequency transform now on the group setting. And you see that our complex value functions u and v, they appear there, but now careful, u of x is complex number, but v hat of eta is operator on Hilbert space. And in formula 6 we have also that eta x, which is like that complex exponential e to I to pi x eta. Fine. Then there is of course the corresponding coherent pseudo-differential quantization, and we can then start convolution smoothing this coherent Riesz transform. It's formula 7. We're formally having that symplectic Fourier transform on a coherent. Then we are multiplying by ambiguity kernel, which is again some sort of operator value function living in the ambiguity plane, and then we take inverse symplectic Fourier transform. This makes sense. Well, in Euclidean space, this is what you usually basically do. Only you start typically with linear transform, but you can do it with coherent like here. And then formula 8 is presenting that definition of quantization, pseudo-differential operators corresponding to symbols. And now what is important to notice is that in that group case, there is some sort of time frequency translation invariance there. That all the information about that time frequency transform, which is defined here in formula 7, is actually already encoded in one point in that time frequency plane, like in Euclidean space. So I'm taking a very specific point. E is neutral element of the group, and that epsilon, funny epsilon, is the trivial representation of the group. The easiest kind of thing. And from that meager information on test functions, this calligraphic S is like Schwarz test functions on the group. Usual Schwarz functions on the Euclidean space, and so-called Schwarz-Bruhat spaces on the locally compact group. Okay, so this is nice to know that there is some sort of invariance, even though you don't have any more translations in the frequency variables, strictly speaking. Then some mapping properties. So there will be like boundedness on L2 in usual sense in terms of those time frequency transforms to the differential operators. And then systematically different characterization results, which are partly also part of these results are new on Euclidean spaces. Many properties are somehow known for many decades in Euclidean spaces. But there is some sort of systematic background framework that is not yet somehow kind of common knowledge, but I hope that after this is published, then people would keep eye on these things. So I'm having several theorems about symmetry, normalization, margins, and time and frequency, positivity, unitarity, and inner invariance of 2D difference operators and corresponding time frequency transforms. And all of those theorems are then having A, B, C, D kind of logical equivalence that I'm having first some innocent looking property, then this generalizes to some general nice property of time frequency transforms, then it's the same for quantization of 2D difference operators, and then maybe some kernel property. And all of these results are like that. I'm having those Schwarz-like test functions. I'm having points in time frequency gate plane, ambiguity plane, test signals, nice symbols for 2D difference operators. And for example, here is some symmetry theorem about symmetry of time frequency transforms, which is stating that, for example, B is symmetry of a time frequency transform is logically equivalent to natural symmetry of 2D difference operator quantization. Normalization theorem is about that sort of inner product between signals is equivalent of integral of time frequency distribution, time frequency transform over the time frequency plane, etc., which corresponds to some sort of trace property of 2D difference operators and so on. Natural kind of things, if you think about the Euclidean space case. Then margins in time and frequency. When you saw those time frequency pictures, you had a horizontal and vertical lines. This is basically, those theorems are talking about those horizontal and vertical line features in the pictures. Positivity, when we have positivity of energy, pointwise positivity in this case is corresponding to natural positivity of the quantization. Unitarity is some sort of preservation of inner product with sort of Hilbert-Schmidt inner product of 2D difference operators corresponds to natural inner product between symbols, etc. And that unitarity theorem can be, for example, this is now formulation for finite groups, all the finite groups. If we have normalized time frequency transform any orthonormal, LQ orthonormal basis of signals, then the sum of energy distributions or time frequency distributions of those signals sums up to identity operator in the time frequency plane. And this result becomes for almost all points if we are giving up that finiteness of the groups and so on. So basically, orthonormal basis uniformly tiles the time frequency plane for any Cohen plus time frequency transform. And then some inner invariance theorem, which doesn't have counterpart in Euclidean space because this is a really non-commutative interesting property. Then some short remark about that why we are using those test functions, those Schwarz-like test functions, and not like some, let's say, Banach spaces of test functions and so on. For example, very natural would be to try to use for compact group, let's say infinite non-commutative compact group. We could try Fourier algebra. Now that non-commutativity is again a problem, it's exploding that Fourier algebra norm, namely that innocent looking operation that we're multiplying group elements x and y to get x times y. That's somehow very nastily behaving on non-commutative groups. So this example is showing that, okay, even nice Cohen-Mittendorf 2D differential quantization is nastily behaving with respect to Fourier algebra. It's that idea of using Fourier algebra here. So it's not a problem at all for those Schwarz test functions. For commutative setting, nothing bad happens here, but for non-commutative groups, it's difficult. Then some sequence of pictures. So I have here some schema how to take the cyclic finite group. Now let's take the very simple commutative group, groups of unity modulo n, and we would put the most natural, the trivial position and momentum operators on the cyclic group. So like if you have hours on the clock, just number the hours like 1, 2, 4, 5, etc. up to 12. That's the most natural way of labeling those points in the cyclic group. And do the same for the Fourier frequency variable. Take those corresponding operators A and B, like here in formula 12, formulate that some sort of uncertainty observable, I2 pi commutator of those. And then see what happens when you take the scaling limits according to that upper diagram. You have two options to go to the Euclidean real line. And you realize that the scaling limit is so-called Born-Jordan time frequency transform. And then due to rotation scaling invariance, this generalizes to d-dimensional case. So kind of the message is Born-Jordan transform is coming naturally from those most natural discretizations of finite cyclic group when you start taking that limit to the Euclidean system. And here depicting that scaling limit thing. So here I'm taking a period of 700. So this is like a modulo 700 arithmetic in time. Yes. And then what happens if I start taking, this is still modulo 700, this is modulo 1400, and so on. And eventually, when you take the limit of those points going to infinity, then the picture becomes much more clear. It's corresponding, this is now discrete version of Born-Jordan time frequency transform. Okay, and then you can do multidimensional visualizations also. So this is, again, Born-Jordan transform somehow kind of infinitesimal version if I concentrate now on the origin of the space in 3 dimensions. And then kind of how photons which are traveling from the origin to different directions. So what are those kind of ambiguities there in the Euclidean space? And then taking this sort of rationale that I'm putting surface, not going now into details due to lack of time, but this is surface which is reflecting photons coming from the origin and always reflecting them into 90-degree angle. So this is some sort of lampshade which is currently in small production and hopefully soon in a little bit larger production. This is prototype printed out in plastic. We're providing them later some metallic and glass versions of this. Also some large scale for lampshades in the ceiling. It's at the same time giving some sort of like equally distributed uniform pleasant light. It's hiding the light source plus saving the material on the lampshade. This is now accepted to conference 2020 bridges, but due to this corona crisis, it will physically appear next year in the conference. So if you're interested, there is a website information where you can get more information about this. So time frequency analysis can be done on quite general groups, and sometimes it's also giving some quite visually nice looking outcomes. Thank you much. I think we have.
Thank you. So we see the time frequency and group analysis in a really applied manner. So this is really, I think you have already printed 3D examples. So once when you have this commercial production, we will be on discounts for purchasing. But anyway, I should say that we have a question for Ville, but from Sanja Konik, but we do not have time. We would like to, and also Ružanski, but anyway, we will distribute your question to Ville. He is also here in Novi Sad, and he will give you an answer via our, I don't know, answers, because we are, I think, do we have time? I think we are a bit late.
2 minutes before the next talk.
2 minutes before the next talk, if we want to, I don't know if...
Just to hear questions.
Okay,
Yes.
let me see.
If I can quickly answer.
Aha, okay, so this is... okay, this is by Ružanski, but how you have... doesn't matter. So, first, nice suit. Okay, so this is your short. Second, this is all... I will read but we should be short for an answer. Okay, this is all on type 1 groups, I suppose.
Yes.
Okay, this is answer. Third, what is the essential difference of this construction from what we call the Weil transform on my paper, Ružanski, with Marius Mantoiu? You have more properties, we had fewer, but construction seems the same. In parentheses, we had it for general locally compact type 1 groups.
Okay, so yes, the short answer is it's a little bit different. So you're having that tau function from G to G, and now quite often there are not so many interesting kinds of tau functions, and kind of that you don't have, strictly speaking, that's a Wegener or Weil quantization in many of these groups. So that kind of I just had to start from some central thing, and what is always there present is collinear there.
Okay. Okay, I think that this will... And then last, on exponential groups, we have Weil quantization. We call it symmetric quantization. In the paper with Marius Mantoiu, will it be of use for you? So exponential groups.
Maybe, let's say here I'm not specifically studying exponential groups. It's just those groups that I was mentioning.
Okay. So we heard the questions and also answers, and
was there still something funny asking?
no, it was it was delivered to us by I don't know how, but anyway, that's all. So thank you once again, everyone. And now let us try go immediately to Jason Vindas. Do we have him on our?
Yes. Do you hear me?
I see you. I
Okay.
see you, Jason. Now we will try to share your screen.
Okay.
Let's see. Okay, we are waiting for your. Okay, now we can see it. Okay, so this is my great pleasure to announce Jason Vindas. He will speak about, as you see, factorization theorems in Denjoy-Carleman classes related to representations of RD plus. So, Jason, please, you can take the control.
Thank you, Nenad, for the introduction. So it's a great pleasure to be speaking here in this conference in honor to our colleague Arpad. So I'll be speaking, as Nenad said, about factorization theorems for modules of in a certain way, ultra-differentiable functions. Okay, so this topic has a long tradition. It goes back to the 30s, to the work of Sigmund and Salland on factorization theorems for function algebras or function modules on the circle. Okay, I'll be speaking later a little bit about the history of the subject, but let me say it has also deep connections with, and also its roots in the study of fundamental solutions for convolution operators, and in particular for PDEs. Okay, so in general, what is a factorization theorem? So we are interested in factorizing functions in terms of convolution. Okay, so a factorization theorem is a purely algebraic statement. Let me say that. So I can just formulate this using pure algebra without analysis, though when we try to show a factorization theorem, of course, we will use analysis. So let me say we take a module M over a non-unital algebra A. So we don't want to have this algebra to have a unit. And then we say that the module M has the strong factorization property if you can factor every element of the module M as a product of an element of the algebra and an element of the module itself. Okay, so that's the strong factorization property, but sometimes we are also interested in a slightly weaker property that we call the weak factorization property. And here, instead of just factorizing as products, you allow also linear combinations. So M is the linear span of A times M. Okay, so once again, this is purely algebraic, and we will be trying to establish, well, I will be discussing modules of functions, common functions occurring in analysis that have one of these properties. And in general, a factorization theorem is a theorem establishing either the strong factorization or the weak factorization. Okay, so and my goal, well, I have basically two goals. Well, actually three goals. I will give you some overview of classical results in the subject, but also I will be presenting some new results that will be a strong factorization theorem of Dixmier-Maliavant type for what we call ultra-differentiable vectors of representations of RD. And also we have established the strong factorization property for many families of convolution modules of ultra-differentiable functions, analytic functions. You might also do it for a smooth function. So it's kind of surprising that most of the modules you consider of smooth and analytic functions, they will have the factorization properties. And I should say this is joint work with Andreas de Brouwer and Bojan Prangowski. Okay, so some short introduction. So let me take a short tour into factorization in classical function algebras. So as I said before, the subject goes back to the work of Salem and Sigmund in the 30s, also the 40s. But in our direction, I will be interested in Rn. So let me mention that Rudin was the first to show this non-trivial factorization theorem for L1. So basically, Rudin showed that you can write L1 as the convolution of L1 and itself. And this was in 50, so the multidimensional case was in 1958, and the one-dimensional case in 1957. A year later, Paul Cohen got interested in the topic, and he extended the result to the function algebra of a locally compact group. Okay, so you might establish this in a locally compact group. And by the way, when I write convolution on non-abelian group, I always mean left convolution, but of course you might do it for right convolution. But let us make that convention. So convolution is left convolution. And so also a few years later, then Hewitt extended the Cohen factorization theorem, actually using the same technique as Cohen, to prove factorization theorems for Banach modules. Actually Banach algebras, but you can do it for Banach modules. And one can show this type of Cohen-Hewitt factorization theorems for many classes of Riesz modules or other topological modules. But there is an essential hypothesis that always occurs in this type of Cohen-Hewitt factorization theorem, and that is the existence, I won't say what it is, but it's the existence of approximative units on the algebra under consideration. So basically, you don't have a unit in the algebra because otherwise the factorization theorem is trivial. You just use the unit to factorize, but you have the existence of nets of elements of the algebra converging to what you will expect to be a unit in a bounded way. So I'm not being precise, and I don't want to be precise. What I want to say now is that there is also an interest, on the other hand, in factorizing just not function algebras, not classical function algebras, but also spaces of smooth functions, which might have a different structure from being a Banach space. And in this case, all this machinery, nice machinery of Cohen-Hewitt type factorization theorems will fail, because in most algebras, interesting algebras of smooth functions that are non-Banach spaces, you won't be able to find these bounded approximative units. Okay, so all this theory will fail. Now let me point out a historical example of a factorization problem in algebras of smooth functions or modules of smooth functions. In this case, that's an algebra. So perhaps the subject was deeply influenced by the following question. That's a question posed by Aaron Price in 1960. So he was interested in the space, the test function space of smooth functions, so smooth compactly supported functions D, and he was asking whether you might factorize this space as D convolved with D. Okay, so it's a very natural question when you are looking for example, fundamental solutions for convolution operators with kernels in D, right? That you might try to relate that question to the search of fundamental solutions. Okay, so there were a lot of developments around this question, this open problem, and perhaps one of the first developments was in 1978 by these three guys, Ruel, Squires, and Taylor. They showed not the strong factorization property. So what Aaron Price was asking in my language, in the definition I gave at the beginning, is whether D has the strong factorization property. These guys, they were able to show not the strong factorization property, but the weak factorization property, where instead of just considering convolution products, you consider also linear span of convolution products. Okay, they were able to do that, but moreover, they made another step forward in this conjecture or problem of Aaron Price, and they show that if the dimension is bigger or equal to 3, then actually you never have the strong factorization property. Okay, so this was a nice paper. Then to solve this, you need to use a lot of machinery of several complex variables. The question remained open for some time for the general case, but let me just add that a year later, Dijksmuurt and Maliavan gave a negative answer for dimension 2. And then the question remained open for 20 years. And then this guy, Kametov, showed in 1999 that in the one-dimensional case, the property does hold. Okay, this is quite surprising. Okay, and his paper is a sort of tour de force into the analysis of zeros, the distribution of zeros of entire functions, because that's basically what you have to do. If you take Fourier transform, the problem is nothing but splitting the zeros of a function of the Fourier transform of a compactly supported function, which is of course an entire function of exponential type 0, basically. Okay, and moreover, several authors extended this work into the direction of another important test function space of smooth functions, the Schwarz space S. So I gave here a list of names of people who showed independently the factorization theorem for S. So S you might factor as S convolved with S. Okay, so this is about factorizing some smooth, some modules, or no, in this case, algebras of smooth functions on RD. But I mentioned here the work of Dijksmuurt and Maliavan, and actually they went a little bit further and they considered Lie groups, factorization in Lie groups. So what they did was to consider, well, let me just briefly say what they said, what they showed. So they show that if you have a real connected Lie group, then you might have the weak factorization property for space D. And when you have an additional property of your group, when you have an important group, you might factor also the Schwarz space, which is well defined in this case, actually. Now, let me just say that still they went further and they consider factorization of modulus induced by representation on Lie groups. And just to be sure that we all know what I mean by a representation, let me just say that I don't work with unitary representations. They didn't either. We are interested in general topological vector spaces, in particular, well, let's say locally convex Hausdorff spaces. Later, we impose to the space to be sequentially complete. So a representation is just as usual as you expect a homomorphism from the group into the group of isomorphisms on this locally convex Hausdorff space, and you ask it to be separately continuous. Okay, And then what Dijkstra and Maliavand factored out were not vectors in the space on which you define the representation, but they were factoring the so-called smooth vectors. So you call in general a vector of the space E, you have a representation of G, the group G on E, you call it a smooth if the orbit mapping of this vector, the orbit mapping under the representation is a C-infinity function. Okay, and let us denote by E infinity the space of smooth vectors. Okay, so Maliavand and Dijkstra show the following. Given the representation, you might induce an action of the space of completely supported smooth functions on the space of smooth vectors of the representation. The action is actually very easy to define, is given by this formula in this box. Okay, so you take f, a completely supported function, and you want to say what pi is an induced action, I will define now, what this induced action is on E. So you basically put, let little pi to act on E, so you consider the orbit mapping over here, and then you multiply by fg, and then you integrate over the group. This is well defined because f is completely supported. Okay, you might use a Riemann integral or a Wick integral or whatever integral you want for vector value functions. Moreover, if you have growth properties of G, if you know some growth properties of G, you might define this for more general functions than just completely supported functions. For example, if you have a Banach representation and it's bounded, for example, a unitary representation, and your group G is nilpotent, then you can make sense out of this integral for Schwarz functions in the group. Okay, and just to write the work, what they showed is that if you have a Riesz space, this is important for them, then the space of smooth factors has the weak factorization property, because you can view it as a module via this action here, big pi. So you have the weak factorization property, but moreover, you have a Hilbert space and the representation is unitary and G is nilpotent, then you can show the strong factorization property with respect to the Schwarz space. Okay, so this is a classical work from 1979, and recently people have got interested in the so-called space of analytic vectors. So you say that a vector is analytic if its orbit mapping is an analytic map. We work with Lie groups, so this makes sense. And E omega is the space of analytic vectors. Now I see my time is running out and I plan too much, so I will just go to one theorem we showed eventually in a couple of minutes. It is important here that now you will work, we want to factor out not with respect to smooth completely supported functions, so the integral I showed before here in the box should be well defined. So we have to restrict our representations. So a representation is called an F representation if E is a Riesz space, and you have this property. Whenever you have a basis of continuous semi-norms, so that when you restrict, when you view your representation as an action on the semi-norm space, E provided with Pn, it goes into E provided with Pn in a continuous fashion. Okay? And for F representations, basically you get that the representation has exponential growth, so you can define an action of the algebra of exponentially rapidly decreasing analytic functions on the group into the space of analytic vectors. And these guys in 2012 showed the weak factorization property for analytic vectors of a representation in case you have an F representation with respect to the algebra I just talked about, the exponentially rapidly decreasing analytic functions. Well, they show the weak factorization property, but they also conjecture that it might be expectable to have the strong factorization property. They establish it for Banach representations in the case when the group is RD, but not for general representations. And what we did recently was to solve this conjecture. Actually, it has a positive answer in the case of when the group is RD. Okay, so now I was talking about this algebra. Let me say precisely what it is on RD. It's easy to define. So the algebra A RD is the space of real analytic functions that you can extend to a tube neighborhood of the real line, of the Euclidean space RD. And on this truth neighborhood, you have super exponential growth in the sense that functions there decay faster than any exponential with respect to the real part of the variable. Okay, and we were able to show this theorem for F representations of RD. You might factor out in a strong manner the space of of analytic vectors. Okay, so you have the strong factorization property for this space. So our results actually, this is just a particular case of a more general result we were able to show. We were able to show things beyond F representations. I won't define what things are, but we did it for what we called, and we introduced what we call projective generalized Proto-Banach representations. So they work well with projective limits, as you might expect from the name, and inductive, which might work well with inductive limits of locally convex spaces, certain ones, inductive generalized Proto-Banach representations. Actually, we show this for not only analytic vectors, but we define the spaces of Denjoy-Carleman vectors, which I won't introduce, but you might imagine how to define them. So let me just go quickly to, okay, so we have Denjoy-Carleman vectors, and we show the factorization property, also strong factorization property for Denjoy-Carleman vectors if you consider algebras of ultra-differentiable functions with super exponential growth, as you see there. So they are the analogs of some an algebra we saw in the talk of Nenad, K1, that's the space of smooth functions of exponentially rapidly decreasing functions. Here we use the ultra-differential version. And this covers the case of analytic functions, of course. And just one example to finish with things you might factor. So if you take E as a weighted LP space, this is a very particular case. We might do this for any translation invariant space of ultra distributions, basically, on RD. But if you consider a weight function with this regularity property, so it's just moderated with respect to the exponential function, basically. So additive or submultiplicative with additive with respect to the exponential function, and you consider the associated LP weighted space as E, as your vector space, and then you let the translation group act here on you induce a representation just by using the translation group. This is supposed to be RD, and then you define, you compute the ultra differential vectors, then you end up with these classical weighted spaces, and you have the factorization property for such spaces. So thank you very much. These are just some references about our work and related works. Thank you.
Okay, so let's thank Jason. So do we have any questions? Maybe Stevan?
This was very nice. Tell me something. Can you factorize if you have twisted convolution, for example, if you consider some other?
Yes, I didn't hear. Can I factorize what?
If you
twisted convolution. Twisted convolution. This is another type of convolution. Twisted. Okay.
Nenad, can you repeat the question, because the audio is I don't hear so well actually.
So if you put, instead of ordinary convolution, if you put twisted convolution, can you say something about this?
Yes, I conjecture is true. Yeah, we don't have a proof. This is the first step forward. But yes. Actually, we believe we can put any nilpotent group. So the Heisenberg group, it's fine. We think. So yes.
Okay.
The answer is yes. I believe, but we have no proof yet.
Okay. So
I have a short comment.
Again.
B?
We also have one more question.
Okay. Okay, there is a question, another question for you, Jason.
To Jason, indeed, the space of smooth vectors of a nilpotent group is the Schwarz space. So for more general groups, this is true for Schwarz space or for smooth vectors. That is the first. Or is it also the same space?
Wait, so you want the Schwarz space? No, we can do it better. We can do it better. So we don't need polynomial decay. We can do it with respect to super exponential decay. So we can define this space. Yeah, so this space K on the group might not be the Schwarz space. It might be a much better space, actually. If I think that was the question. And the other one was. Well,
Or is it the same? So that's actually one question. This is true for Schwarz space or for smooth vectors, or is it also the same space?
For smooth vectors, we can also do it with respect to smooth exponentially decreasing functions. Yes, this is possible. Okay. We have not written down things, but we have done it. We have done it. Yes.
Okay. So thank you. Again?
I realize that we have some problems with questions, so then I will explain what everyone should do.
So this is organizational information. If you want to pose a question through chat, then please choose the option all participants. Since we had the experience that question which was sent by chat to attendees, we couldn't see it. So if anyone wants to ask another question today or tomorrow, please in chat use the option all participants, so the organizers could see these questions. Otherwise, it is somehow blinded for us. Anyway, let's try to see. Thank you, Jason, once again. Let's try to see if Diana Stoeva is online.
Yes, I'm here. Yeah.
Yes, I hear your voice. Now I see you, and we are waiting for you to share your screen.
Okay.
And then when we see your slides, then I will announce your talk.
Okay, I will try now. Screen share.
Okay, your screen appeared, but now we see the background photo. So, and now you open the file. Okay.
Full screen mode.
Yes, you can put it full screen. Anyway, let us announce the last speaker of this morning session before lunch break. Diana Stoeva will give a lecture on recent characterization of Riesz spaces. Please, Diana.
Thank you. Thank you. Thanks to the entire Novi Sad team who organized this conference in the memory of Professor Arpad Takaci. My talk is also dedicated to his memory. I may say that I met him already during my first visit in Novi Sad, which was in 2005, quite many years already. And this is a photo from this first visit. Professor Arpad Takaci, Professor Mirjana Stojanovic, who is unfortunately not alive. She died also several years ago. And with Professor Pilipovic and Professor Robert Guggenberger. I may say that I have very good memories with Professor Arpad Takaci. He was very friendly, with very nice character, very kind person. Whenever he meets me at the corridor of the university or wherever at conference, he always stops and talks, and he was really very friendly person and very kind person. And everyone will miss him, but we will never forget him, so he will continue live in our memories. So I'm going to talk now about some recent characterizations of Riesz spaces. So a short overview of my talk. I will just give the notation and the basic notions which I'm going to use. Then I will recall the definition of Riesz spaces and classical characterizations which are known. And then my focus will be actually on one of these characterizations, the one which concerns complete bi-orthogonal sequences. And then I'm going to share in this short talk the main result, the progress on this characterization, and then I will mention some possible applications. Okay, so H will denote a Hilbert space, EK will denote an orthonormal basis, F and big G will denote sequences with elements from the Hilbert space. Then let's just recall what is Bessel sequence in a Hilbert space. It's a sequence where this inner product, the L2 norm of these elements, is bounded from above with some positive constants. And then minimal sequence, it's a sequence which has the property that every element is not in the closed linear span of the rest of the elements. So this is somehow the notions which will be used in the talk. And then let's now go to the Riesz spaces concept. So Riesz spaces are sequences which are images of an orthonormal basis via bounded bijective operator on the Hilbert space. So just in finite dimensional space, this is kind of using just a basis, because in every finite dimensional space, every complete system which is minimal as well is actually a Riesz spaces. So just look at the two-dimensional space. You forget about orthogonality and you forget about normality, and then you obtain the concept of a Riesz spaces. So just two vectors, for example, phi1 and phi2. So it is a Schauder basis. You can represent every element in a unique way, just avoiding the properties to require orthogonality or normality. Riesz spaces were introduced by a Russian mathematician, Nina Bari. Actually, she gave in a very short paper just the basic statements which she had about introducing this concept and the main properties. And then in 1951, there was an extension with all the proofs and the details. So now I'm going to mention some of the many equivalences to the concept of Riesz spaces. Some of them were available already in the first papers of Nina Bari and a paper of Gelfand also at that time, 1951. And some of them were obtained later. So a sequence Fk is a Riesz basis if and only if it's a bounded unconditional basis, if and only if it has the property that it's a Schauder basis, so that whenever you have convergence of series of such form, this happens if and only if the coefficients are in small L2 space. Another equivalence of a Riesz spaces, it's that the sequence being complete and the Gram matrix form in this way determines the bounded bijective operator on the sequence space L2. So now I'm coming to another characterization which actually can be found in the literature also as a definition of a Riesz basis instead of the image of an orthonormal basis via bounded bijection. So this is a complete sequence which has the properties that the norm of these elements are bounded from above and below with some positive constants A and B. And this property is enough to be required for all finite sequences, because then it automatically implies that it is also valid actually for all the sequences in L2. Okay, another characterization of a Riesz basis is that Fk is a Riesz basis if and only if it is a complete Bessel sequence in the space, and it has a biorthogonal sequence which has the same properties, like being also complete Bessel sequence. So if we compare R5 and R6, actually the Yappa inequality in this, I think it was 1,1. I cannot see it right now because the chart is still there. But the right inequality, the Yappa inequality, being valid for all elements in L2, for all sequences in L2, this is actually equivalent to the Bessel property. So now actually the difference between R5 and R6 comes to the lower condition here, and then the completeness of Fk with such properties of the biorthogonal sequence as well. So in general, if you try to verify some sequence, whether it's a Riesz basis or not, the upper inequality is easier to check. The more difficult part to check is the lower inequality. And from that point of view, R6 somehow makes it a little bit easier because you, let me see, okay, because you changed the more restrictive condition about this inequality with less restrictive condition to having completeness. But also then you require one more completeness of the orthogonal sequence. And then completeness is kind of, okay, less restrictive, but still also difficult to check for sequences, for some sequences. Okay, another famous characterization is R7, which is actually, if we compare R6 and R7, we again have completeness of Fk and having the orthogonal sequence, which is also complete. And now the differences are between having Bessel property in Fk and Gk and having these inequalities fulfilled, the convergence of this series, which actually is equivalent to the Bessel property. So somehow R6 and R7 differ only comparing the Bessel property and these inequalities, which are equivalent. And so my focus will be now on the property R6. This characterization, which uses complete Bessel sequence, with orthogonal, which has the same property. And as I mentioned, somehow it kind of makes it easier, the verification of the Riesz basis property, but still not very easy because completeness is still a task. For example, for Gabo systems, it's a not easy problem to determine whether Gabo system is complete or not, for certain systems, of course. Okay, so the main result which I'm going to share is that actually one can remove completely one of the conditions in this R6. So actually R6 turned out to be not having independent, not having minimal conditions, but having one extra condition. So what actually you can do, you can completely remove either the completeness of Fk or the completeness of Gk in this characterization. And then once you erase this, then the rest of the conditions are then minimal. So then you cannot erase second condition, but you can very well remove one of the completeness conditions. So why this is important? Well, from one point of view, it's like it is characterization of a Riesz basis. So it should be good to have a characterization which does not contain extra conditions, and then this one reduces R6 to a characterization which does not contain extra conditions. Also, it simplifies the verification. So if you want to check the Riesz basis property, instead of checking two completeness conditions, then you check just one completeness condition, either of the given Fk or its bi-orthogonal sequence. And then actually one can observe that this characterization can also lead to immediate conclusions which cannot be concluded if you use the property R6, the characterization with R6. So for example, if you take the Gaussian and if you use sequence which is of uniformly separated points from R2, then if you take this irregular Gabo system, so you take the window G, you take all the translations and then all the modulations according to the elements in this lambda set, then what is known is that this system cannot be a Riesz basis for L2. However, it is a Bessel sequence, it satisfies this upper inequality. And for specific sets of lambda, it is minimal and complete. For example, if you consider this set lambda, -1, 0, the dots in R2, -1, 0, 1, 0, and then you take the axis and you take appropriate numbers on this axis, x or y, then actually the Gabo system is minimal and complete. Another possibility is if you take a lattice, for example, you take the lattice Z by Z or any lattice AZ by BZ where A and B is 1. So you take the critical density. Then you have complete Gabo system, but it is not minimal. And it is not minimal by one extra point. So if you remove one point, then you get complete minimal system. So these are just some examples of cases where the corresponding Gabo system is complete and minimal, so it has a bi-orthogonal system. And then you can use the new result to show that the bi-orthogonal sequence, the bi-orthogonal system of this irregular Gabo system is not Bessel, which actually you cannot immediately obtain if you use the characterization R6 up to now. So if you use the non-characterization R6, what we have that the Gabo system is not a Riesz basis, so this must fail. And we know that we have the Gabo system being complete, Bessel, it has bi-orthogonal, but then your conclusion would be that it is either non-complete or non-Bessel. And then if you use the new characterization in the way removing the completeness of GK, then actually you can immediately conclude that the bi-orthogonal sequence is not Bessel sequence. And we also believe that actually for the systems with specific structure can also be somehow characterized there, or their bi-orthogonal systems using this simpler characterization. And that is what I was planning to tell. Thank you very much for your attention. Okay. I hope you find it.
So thank you, Diana. As usual, we had a very clear presentation. So far, I didn't see questions, but maybe Professor Pilipovic.
I'd like to ask you if you little move from Riesz basis with some well-localized frame. Can you get some result in that case? How it works? I mean, because we did some things with localization. How it looks like? Is it more difficult? Did you consider this?
Yeah, not yet, but yes, this would be really nice to consider, as yes, we have worked with localized frames, and there we use localization according to specific Riesz basis. So this might be an interesting question to consider. I have not looked at this point yet, but this would be a good point. Thank you.
Okay. Okay, there is a question from Peter.
Hey. Yes.
Okay, yes, you are here. Okay, let's hear the question.
So if you can remove, so if you can remove the completeness assumption for the bi-orthogonal sequence, this means that there is not a unique. You can, or in another way, you can delete the uniqueness property for the bi-orthogonal sequence, right?
No, because actually the completeness is, it follows automatically. So I erased it in order to prove that this implies the Riesz basis property, but it is not that it is not valid. It is automatically fulfilled after you have the other conditions. So I erased it in order to have, I mean, to show that without completeness, we actually can show that it follows.
I understand. What I'm saying is, instead of well, reducing the assumption for example, for an so you reduce the assumption of complete bi-orthogonal sequence to just bi-orthogonal sequence, right?
Well, I assume that one of the bi-orthogonal sequences is complete and Bessel.
Yes.
And the other one is just Bessel. So this is the assumption. I don't assume. So I assume Bessel property for both sequences.
Yes.
Completeness just for one of them. And then actually what comes out is that the other sequence must be complete. It cannot be complete.
But what I'm saying is, so a sequence has a bi-orthogonal sequence that is unique if and only if it's complete. So that would be a reformulation So you could, in the assumption, well, reformulate it by, yeah, not including a uniqueness. Do you know what I mean?
I have not mentioned uniqueness. Yeah, what? No, I don't understand what you mean. I do not say uniqueness.
Right?
Yes, I don't assume uniqueness. I just assume completeness. Yes.
Let me. So there's this result that if a sequence has a orthogonal sequence, this is unique if and only if the first one was complete. So maybe you can formulate something like that. Maybe you can see it in this way.
You wish to get some reformulations of the one about completeness and minimal. So yes, if it is complete and minimal, it was unique by orthogonal. Okay, I may have a look. Yeah, thank you. Thanks.
Okay.
Okay. So thank you, Peter, for this hint. And let's thank again to all the speakers of this morning session, and we have a lunch break, and then we will resume at 3 o'clock, some minutes before 3 o'clock. So thanks to speakers again.
Yeah, sorry, you cannot join us down the stairs. But hope that you will enjoy it by yourself.
Hello, everyone. Are we ready to resume?
Yes, I'm here.
Okay, so
Can
Brian
I
is here.
share the
He's ready. Okay, so after this lunch break, I'm welcoming all of you again, and we are now ready.